Good morning. Let us continue our lecture devoted to application of Gaussian stochastic calculus to partial stochastic differential equation, which arise as a result of second quantization applied to some functionals from diffusion processes. Today we will consider the results of second quantization of such functionals, and let me begin with the following statement. Suppose that we have already usual for us abstract picture. So we have a Hilbert space which is real and separate and infinitely dimensional as usual. Here we have a Gaussian white noise psi, and I suppose that sigma field of random events is generated by this psi. Now let us consider additional metric space X rho, which is complete separable metric space. Suppose that X is a random element. In this space, in X. When I am saying a random element, I suppose, as usual we did, that X is measured mapping from the probability space to space X, which is equipped with the Borel sigma field, which is respect to this distance rho. So we have such random element. Now let us take operator C in our Hilbert space. Consider operator C, which is a continuous linear operator in H, such that norm of C is less or equal than 1. And suppose that we consider operator of second quantization. We know that with every operator with this condition, we can associate operator of second quantization, which is acting in the space of square integrate functionals from the initial white noise psi. Now let us consider function f, which is let it be simply from X to R, bounded and measured. Then we can consider the random variable f of x. Since f is bounded, it is square integrate, and one can apply operator of second quantization to this random variable fx. And I'm claiming, this is a statement of the lemma, that it can be expressed as the integral over x f u nu du, where nu is a random probability measure. On x. Let me recall you what is random probability measure. Actually, we discussed such questions, but it is useful to do this now. So, nu is a mapping from omega multiplied on the Borel sigma field in x to 0, 1, such that for any delta which is a Borel subset of our space X, this new let me don't write this argument omega is random variable and secondly for any omega which belongs to our probability space, new omega is a probability measure on B. This is just a reminder of what we are calling by random probability measure. And the statement, let me again write the statement of the lemma. It looks like we have random element, is a random element in X, then there exists such new random measure, random probability measure that for all f which are bounded and measured, we have the application of second quantization to f of x is the integral over x f u nu d. Actually, if we recall that we have a nice representation of the operators of second quantization as a conditional expectation, it is nothing surprising here. Because if it is a conditional expectation, then maybe nu is just conditional distribution of x. It is true. But when we discuss it, this representation, we discuss it for random variables. Let me recall you what we did. So we considered psi prime, which is independent of psi and also white noise in H, and we discussed that if we have random variable alpha, which has an e to inner expansion like sum from 0 to infinity an psi psi psi, then one can define new white noise psi with tilde, which will be equal to c psi plus square root of 1 minus c star c psi prime. Then it will be also white noise. This square root is well defined because of the condition of the norm of C, which is less or equal than 1. Then we discussed that one can consider alpha from psi with tilde, which is defined with the help of the same multilinear Hilbert-Schmidt forms. So it is equal to the sum from n equals 0 to infinity. An psi with tilde and so on. And finally, we got the following representation. We got the following representation for second quantization of the variable alpha. Namely, it occurs that the following formula has the following formula holds. The second quantization gamma c alpha is equal conditional expectation of alpha from psi with tilde with respect to psi. That's all. So one can imagine that due to this representation, we can expect that our lemma holds with the conditional distribution of x with respect to something. Only one difficulty we have there. If we want to apply this approach, we need to understand what is x of psi with tilde. Why I am saying this? Because x now is just a random element. It is not a random variable, so it has no e to inner expansion, and we cannot proceed in the same way, just calculating this e to inner series from new white noise, because as I'm saying again, x has no e to inner series. So this is only one problem which we have to overcome when discussing the proof of the stated lemma. But this is not a very big problem due to the separability of our space. Let me recall you. that our space X capital, X space X capital is complete and separate. Due to this fact, one can find the sequence Fn Fm m is greater or equal than 1 of bounded and measured. Actually, they can be chosen even to be continuous and bounded functions on X, such that they are playing a role of coordinates in this space, namely that for all u v belonging to X, we have the following. If for all n, for all m greater or equal than 0, f m of u is equal to f n of v, then u is equal to v. Yeah? So what we can do, we just can substitute discussing of the elements of maybe very complicated matrix space by the discussion of its coordinates Fm. Such a family Fm can be obtained easily if we recall that this set is separate and complete, and Fm is just suitably modified distance to the points of separability. Please try to construct this sequence as an exercise. This is not too hard. So we have such like coordinates in our space X, and then we can try to proceed as follows. Let us define our measure nu in such a way. So consider gamma c of Fm of X. Consider gamma c of Fm of X. One can say that it is well defined because we said that they are continuous and bounded. So we define a family of such new variables, and now let us know that if Fm is greater or equal than 0, we can choose it in such a way, then gamma c Fm X is also greater or equal than 0. Moreover, one can check that if we have gamma c from the linear combination, the sum from k equal 1 to n capital ak, fk, let me type here x. Then I can check that absolute value of this is less or equal than sup over x of the absolute value of the sum from k equal 1 to n f, excuse me, alpha, not alpha, ak, fk from u. So this means that for linear combinations of these functions, we have a linear non-negative functional defined on these linear combinations such that it satisfies the following relation. Now let us use standard theorem from the measure theory. Due to the separability and completeness of x, it can be checked that it means that there exists random measure nu such that there exists such random measure nu that we have such a relationship. Gamma c from fm x is equal to integral of over x fm u. This is not a final statement. We have to check the same relation for any f. But since then, since we have the probability measure, the technical work can be done. Maybe you remember Coulomb's theorem about the tightness of the probability measure on the complete separate metric space. Then one can consider increasing family of compacts for nu, and then prove that this relation will be true for arbitrary continuous and bounded function, and consequently for arbitrary measured function. I will not to do this because it is a rather technical part, but it can be done. So I just present to you the approach with coordinates in order to understand how we can apply the second quantization to random element x. This is the end of the explanation of idea, not full proof, but idea of the proof of the lemma. And now let us go to applications, because they are very interesting. So let me start with the process, which is the solution to stochastic differential equation. So I will suppose that we have one-dimensional case and good functions a, b, which belong to c 0, 1 r with bounded derivatives. And let us consider the equation dy t is equal to a of yt t plus b yt dwt. This is an ordinary stochastic differential equation. And since our coefficients are very good, then for any initial condition, it has a unique solution, which is adapted to the flow of sigma fields generated by the linear process W. And we know a lot about this process. Namely, we know that Y is Markov process. Namely, if we fix present position of Y, actually due to the existence and uniqueness of the strong solution to stochastic differential equation with such good coefficients, we have the Markov property. But when we began to study Markov chains, Markov processes, we began with the family of transition probabilities and Chapman-Kolmogorov equation. Yeah? So what are transition probabilities now? Let me define. I will fix small x belong to R and time t, t, which is greater or equal to 0. Then I can take function f. I will suppose that this function is of class C2 bounded, namely it has two continuous bounded derivatives. And now let us consider expectation x f of y t. Expectation f of y t. What is this? This is the expectation of our solution to this equation with the initial condition y from 0 equal to x. This x. This is a common notation for the theory of Markov processes. We just fix the starting point for process. We fix initial condition for our stochastic differential equation. So this is an expectation with respect to yt starting from x, and let me denote it as rewrite it as integral of r. Here is f of u, and here is p t x du. So it must be the integral with respect to probability measure, and this probability measure depends on x initial point, t time as a parameters. Yeah? Actually, now these families p t x t is greater or equal than 0, x belong to R are exactly transition probabilities related to our process y, and they satisfy Kolmogorov-Chapman equation. So for any S1, S2, S3, these are moments of the time, and any X belonging to R, we have the following representation. P X maybe we just forgot about this order. Let me just write S2, which I written. Yeah, it is much better, much easier to formulate in such way. Px S1 plus S2, here X and something delta is equal to integral of R P U S2 U delta P X S1 excuse me, I use another notation. Yes. Okay. I repeated this here, the same here. Okay. So Px du. This is Chapman-Kolmogorov equation. It can be very easily interpreted. For our Markov process, probability to start from X and to hit delta at the moment S1 plus S2 is equal to the following probability. We just start from X. For the time S1, we get du, and then for the time S2, from U, we get delta. And we integrate over any possibilities, any possible U. Yeah? So this is a very natural equation, but it leads to the statement that these probabilities organize the semigroup, which is called transition semigroup. And if we consider related operators in the space of functions, it leads to very deep and fruitful theory of Markov semigroup. So what is important for us now, that now, due to the nature of our solution, our process Y, it occurs that these transition probabilities satisfy some interesting parabolic equation, namely if I take those function f, which we discussed, and consider such function u, which depend on x and t, so this is a function of two parameters, x is for r, t is greater or equal than 0, which is defined as an expectation when we start from this x of our f from yt. Then it occurs that this two coordinates function satisfy some parabolic equation, namely du over dt is equal 1/2 of b square x d over dx square u plus d over dx a of x d excuse me. sorry, plus a of x d over dx du. And initial condition u x 0, of course, is equal to f of x. So we have the following parabolic problem for our process y. Let me just recall you that the one partial case is very well known, and if a is equal to 0 and b is equal to just 1, then u is expectation of f of wt, and we just get the well-known Fourier equation for heat equation d u is equal 1/2 of d2 dx square u with the u x0 equal to f of x. And we know a lot of conclusions which can be made relatively to properties of our process y using parabolic equation, or to parabolic equation using the probability properties of y. As the last one, let me recall you that if we have additional assumption that b is greater than 0, then using Malevin calculus, one can check that this solution has this equation has fundamental solution, which of course can be interpreted as a density of the initial process y. So we can use probabilistic arguments just to say something about the purely deterministic equation in partial derivatives. So then, since this picture is so fruitful and useful for both theory of partial differential equations and stochastic differential equations, Markov processes, it looks like it will be interesting to see what we will have when we apply not total expectation, but just conditional expectation. And since we already mentioned today that conditional expectation is just partial case of the second quantization operator in some cases. So today we begin to discuss the application of the second quantization operators to such function. Instead of unconditional expectation, we will look for some conditional distributions of this processes y. So let me begin with this. What we will consider, we will start from the following family of processes. I will denote y x s from T for x belonging to R. S is less or equal than t moments of the time. This is a solution to SD dy t equal a y t dt plus b of yt dwt when it's start at the moment s from the point x. Under our assumptions on the coefficients a and b, it of course exists and is unique. Our equation has unique strong solution now. So I am considering a family of such solutions. And then let me define a random measure. Let me define a random measure. Let me define a random measure nu x s t as follows. For any f which belongs to C2 bounded to R, we just have that gamma c of f of y x s t is equal to integral of R f of nu x s t d. This is the definition of the right hand side. So one can put here notation of the definition. Here we use our lemma, which we mentioned in the beginning of the lecture, and then we got the family of random measures. By the way, if C is equal just 0, so in partial case, when C is equal to 0, then gamma C is just expectation, and in this case, our nu xs C is equal to p t minus s x. This is a transition probability. This means that we can expect several things from this family. Firstly, we have to understand what is the substitution now of the Chapman-Kolmogorov equation for this random measure. And secondly, we have to understand what is the substitution of those parabolic problems which was mentioned for these quantities when we take expectation. So let us begin with the first problem. So what will be an analog of the Kolmogorov-Chapman equation for this family? In order to understand this, let me note the more modern representation of the solution to ordinary stochastic differential equation, which is So let us consider again this equation. dyt is equal a of yt dt plus dyt dwt since we suppose our coefficients are good, then it can be proved that not only we have the solution for fixed initial condition, but that now there exists a flow of solution. A stochastic flow. Namely, it can be proved that now there exists a family phi s t, 0 is less or equal than t. This is a family of random homomorphisms on R such that firstly phi s t of x is exactly the solution to our equation, which start from the point x at the moment s. Secondly, phi s x of course equal to x. Then phi s2 s3 from phi s1 s2 of x equal to phi s1 s3 of x. For phi s1 s2 is equidistributed with phi s1 plus t s2 plus t, and phi s1 s2 phi sn minus 1 sn are independent for s1 less than sn. Actually, these properties seems not to be very surprising. And if we just recall the theory of ordinary differential equation, deterministic theory, then we definitely recall the flow of solutions to equation, and we understand that the existence of such flow and is very helpful, and its properties says a lot about properties of the equation. Just recall the Liouville theorem, which arises when people more than 100 years ago considered three-body problem and discussed a problem about stability of such related equations. Then when we have the volume conservation property for the flow, we cannot expect the one point which can be attractor for our equation. Yeah? So we understand that the existence of such flow is very useful thing. So people in stochastic differential equation prove this. Maybe a good reference is the book of Shinzo Watanabe and Nobuyuki Ikeda on stochastic differential equations, or another very good and much more modern book of Hiroshi Kunita, Stochastic Flows and Stochastic Differential Equations. It must be noted that the inventors of stochastic differential equations who worked at those time in Kiev, Iosif Ilyich Gichman and Anatoly Vladimirovich Skorokhod, proved the existence of the flow in light modification. Such evolutionary properties does not hold totally for all S and X simultaneously. And the regularity property with respect to spatial variable was proved only in L2 or in LP sense. But this idea can be refined, and here you can find a complete proof of this statement. What is interesting for us?
But Nikeda and Watanabe, the omega also depends on T or something, and Nikeda and Watanabe. Only Kunita proved it independently of everything.
You say that they shift omega here.
Yeah, well, no, the omega depends on, so it isn't almost surely for all T, but for, no, not for all T almost surely, but almost surely for all T. So
yeah, I understand. Thank you for this comment. But I think that it was only technical problem for them. Okay, the much stronger result is here. Thank you for the comments. But I just want to point your attention to the last one, property, which is from one side very easy to understand. From other side, it is very helpful for our consideration. So why property 5 holds? Why property 5 holds? Let me recall the equation. So the equation was like this one: dyt equal ayt dt plus db yt dwt dwt, and it is evident that if we want to define the mapping phi S1 S2, then it depends on only increments. Let me say non-formally W is dot on the interval S1, S2. So we, in order to build this random homomorphism, we have to know increments of the process W only on this interval. So now this statement becomes to be trivial, yes, because we just will consider the non-intersecting interval S2, S3, and so on. And we know that W has independent increments. Yeah? So this is very important. Why? Because here we have interesting independency, which we already knew. This random homomorphisms occurs to be not simply independent, but independent in a way which we already mentioned. They depend on the white noise from orthogonal subspaces of L2. So it is very important for us. And let me explain you why. Now, as we have seen, we have a property phi S2, S3 from phi S1, S2 view is equal to phi of S1, S3 view. Let me rewrite this. Yeah? How I will do this? Let us define the delta measures. Delta U S1, S2 will be a delta concentrated at the phi S1, S2 U. Then what is written here? Here is written the following relationship, that if I take F, which is, as we said, bounded on R, then F, this delta U S1, S3, I will use this angle brackets, as usual people doing in physics, when denoting space integral, is equal to here F of phi S2, S3, and here we have delta U S1, S2. Yes. Now let me recall you that here we have something like a scalar product. Maybe you just have such experience from physics when people say this is like scalar products, but between function and measure. Moreover, they are independent. So let me put here star. You remember that if we have the independent in this geometric sense, this depends from one orthogonal subspace, from one family of Wiener increments, this depends from other family, then their product is exactly the weak product, yes? So I can put here star. And then let me apply second quantization, gamma C. You remember that second quantization commute with weak product. So we will have the following. Gamma C here, and here we will have gamma C from this delta U S1 S2. That's all. We now are on a position to get Chapman-Kolmogorov for our measures nu, because maybe you can imagine this will be related to measure nu. This is related to other measure nu in here, and we will have a convolution in the sense of weak product. This will be the answer. But this answer we will study at the next lecture. For today, that's all. Thank you for attention. And maybe somebody have questions or comments, please. Okay, if no, thank you and bye for the next week.